Okay, thanks. First, I want to thank the organizers for including me in this session. And I want to talk today about some simulations we've been working on to directly model volatile sputtering and transport in permanently shadowed craters at the lunar poles. And as the title suggests, we're really interested in how the solar wind interacts with permanently shadowed regions at the poles. Do the protons in the solar wind sputter material away to the implant? How does this depend on crater morphology? How does topography modulate the sputtering process within these regions? And we're basically, to start understanding this, we can start by looking at the global situation on the moon, where we have solar wind flowing out from the sun. It hits the moon and creates a wake that extends many lunar radii downstream. So this is a plasma wake that, right, on a global scale. So we think the same sort of thing happens right at the poles in lunar craters, and this affects the way that protons flow into these craters, and we can simulate this. And we've done a lot of this work over the last couple of years. So here's the expectation. Basically, I've shown this movie before, but just to remind folks, basically this is the solar wind. It's been obstructed upstream in the lower region, like maybe the solar wind has hit a crater rim, and right. So we have protons and electrons, and they're flowing from left to right. And the electrons are much faster than the protons. They rush into the crater and create a charge separation. And this creates a downward electric field, which then pulls the protons into the crater. And you can imagine this process as the solar wind convects downstream past the rim of the crater and farther downstream. It creates a wake, and it will divert protons toward the surface where they will hit and sputter or implant, depending on the properties of the surface. So here's a recent simulation I ran. We had been doing a lot with particle and cell simulations in the last couple of years, and so we've developed a new Treecode to model plasma wake formation at the lunar poles. This is kind of it's like a particle and cell code where we're modeling protons, electrons, all these particles as they flow around under their self-consistent E fields. But it's a very adaptive technique that can handle large gradients such as day-night boundaries and arbitrarily shaped surfaces. This is one of the first simulations we've run. So you can see the proton, electron, and photoelectron densities here. Dark is more particles, light is less, and you can clearly see a wake forming, especially in the proton and electron densities at that first crater rim. And some of the protons are diverted into the crater and they hit the surface, the interior surface. And we've done some comparisons with theory. Things compare nicely in both the wake, that's sort of the dotted line, what we would expect for the shape of the wake, and upstream where we have photoelectrons coming off, some of the electrostatic structure there agrees well. But what I'm really focusing on is not the plasma physics today, but what happens when those protons hit the surface, and how can we model that in our Treecode. So, like I've been saying, we've been working a lot on how does topography modulate the proton flux via wake formation in these polar craters. We can do a lot of this via these plasma simulations, and we can apply some theory. But really now, what's the next step to look at sputtering? Is the solar wind a source or loss of protons in these craters? Right, and so we could also have chemical processes in the soil after we get the protons in there, which is sort of the third box down here. But I'm going to focus today on the first two steps here. Modeling the proton flux and then looking at how that drives sputtering or whether or not it implants various products. So here's a result, same simulation I showed before. We have the wake clearly shown in the proton concentration on the top panel. And you can see this is H2 being sputtered away. Basically, you can see upstream, right, this is right at the pole where the solar wind's flowing from left to right. You can see the protons hitting that upstream crater rim and releasing H2. You have an H2 concentration in the middle panel and velocity in the bottom panel. And then also, some of the protons are diverted into the crater, and they hit the sort of downstream rim at about positive 1,000 meters in X, and that also drives some sputtering. And this is using Zimmerman 1969 sputtering distribution, and right, so we get these velocities that are far exceed the escape velocity for the moon. So if we multiply the concentration by the velocity, we can get a flux to get an idea of how many of these particles are leaving per time per area versus how many protons are coming in, and decide, get a feel for where the incoming protons outweigh the ones that are leaving, the H2 molecules that are leaving. So here I show the flux at the top in terms of the solar wind thermal flux, and basically you can see in the middle panel, basically everywhere the yield is about 0.1, and I've actually underestimated it in the code by, it should be about 0.6. But this is a first cut, and you can see that the incoming protons only release about 0.1 H2 molecules per incoming atom. I'm sorry, per incoming proton, and so this is an effective H source. And then downstream, there's also an effective H source. And so you can see the red in the bottom panel is actually where we've liberated H2 from the downstream crater rim, and it's traveled upstream and sort of coated the interior of the crater. But that's a very small contribution. So like I said, there's still a yield factor that's a little bit off here, and scaling that around there's a little bit more work needs to be done on that. So one thing we're interested in is really what if there's already some ice in the crater? Can we model the the sputtering and learn something about that? And here's an older simulation we've done where the protons are going in and being diverted toward the crater floor, and you can see these are actually H2O, just assuming an H2O ice surface as a proxy for some volatile population. And you can see them being released and going upstream and sort of coating the crater wall. In this case, there's nothing, there's no ice in the surface upstream. So we can start to look at this, is this actually over a long time going to represent a net accumulation or a net loss of water in the surface? And actually getting close to the end here, basically the same code. We want to continue this kind of work with the wake formation and looking at how topography could modulate sputtering processes at the lunar poles. We're going to continue that in the context of small airless bodies. And so here's the simulation, again using the same code where we have a small asteroid, maybe 150 meters in effective diameter, but it's this irregular shape. And it's going through the solar wind here. The solar wind's going from left to right. The sun is actually illuminating it from the left. And we get a nice wake, which you can see actually a few mini wakes, where the body is actually obstructing the flow of solar wind. So not only sort of at the top and bottom of the object, but also in the little cusp at the bottom, sort of in the middle part of the asteroid, where you go from a day-to-night boundary. And a lot of this plasma physics is matching up with what we would expect from theory and from previous work on photoelectron sheaths. So I've animated this actually as this thing tumbles through space. So here you're looking at electric field magnitude as this asteroid tumbles through space. And one thing we're wondering in the context of the present talk is, what if we have little concentrations of some volatiles maybe in the dimples in this asteroid, which would represent effective craters. As this thing spins around and is bombarded by protons on the day side, would this thing give off like spirals of volatiles that go out through space, and then we could potentially, grab those with an asteroid mission, with a spacecraft near the asteroid, and learn something about the spatial distribution of volatiles on the asteroid or the composition. So these are simulations we want to start looking at in the near future. Oops. See if I can get out of this. Okay, so I'm actually already at the end. But what I hope I showed today is that we have developed this versatile software tool for simulating the plasma environment at kilometer scale airless topography, including polar permanently shadowed craters at the moon and asteroids that are small to medium size, sub-kilometer scale. And this also includes sun shadow boundaries. There's a lot of interesting plasma physics there. And we model the sputtering sources and losses on equal footing with the plasma physics. And some more work needs to be done in nailing down the physical details of the sputtering model for various species. But I think all the the software framework is there. We just need to nail down some of these details. And of course, I haven't included any thermal or meteorite-driven release mechanisms or looked at other than typical solar wind conditions. But I think this is a promising code, and looking forward to using it in these different contexts. Okay, thank you. Let me leave it at that.
All right, very good, Mike. I think we have a question that's come up from Sue. Hey, Mike, what about at craters located slightly off the poles, so you will have photoelectrons?
Right. If I included it here, we've started to look at that, right? So all of these simulations did have photoelectrons. I'd have to look. But we have done some mid-latitude craters as well, where you have a partially illuminated crater floor, but part of it's in shadow. So that, the code is definitely capable of handling that kind of stuff and looking at sputtering in those kinds of contexts.
And I think the next speaker soon should probably get online with his webcam. So I think that's the next speaker coming up. Well, very good. Let's see any other